So let's move to the next question. The question is given as a 0.5 meter long flat surface is covered with water, is placed with internal air at 105 Kelvin and 1 atmosphere is blown over it at 13 meter per second. The kinematic viscosity of air is 1.4 into 10 raised to power minus 5 meter square per second, and the mass diffusivity of water vapor in air is given as 2.5 into 10 raised to power minus 5 meter square per second. The partial pressure of water vapor on the surface is 50 kilopascal. Calculate the total water loss per hour per meter width of plate in kgs, and calculate the heat transfer coefficient if the heat capacity of air is 1.005 kilojoule per kg Kelvin. The viscosity of air is 1.6 into 10 raised to power minus 5 kg per meter per second, and the Prandtl number is given as 0.7. So in this question, first we will understand what is given in this question. So a long flat plate is given which is covered with water and air is blowing over it. The temperature of the air is given as 0.5 Kelvin and 1 atmosphere, and the velocity of the wind is 13 meter per second. So the wind is blowing over the flat plate, and in this process a mass transfer will take place. So the water vapor on the surface will move into the air and the concentration on the surface will decrease. So we have to calculate how much amount of water is lost from the surface and move to the air. So to calculate that, we need to calculate mass flux, mass flow rate, and then from mass flow rate we can calculate the total water loss per hour per meter width of plate. So first we will write the given data from the question. So now we have written down the given data. We have written that temperature of the air is 105 Kelvin, pressure is 1 atmosphere, kinematic viscosity is given as 1.4 into 10 raised to power minus 5 meter square per second, diffusivity of air water vapor in air is given as 2.5 into 10 raised to power minus 5 meter square per second, partial pressure of water vapor at the surface is given as 50 kilopascal, and heat capacity is also given here as 1.005 kilojoule per kg Kelvin. Viscosity of air is given as 1.6 into 10 raised to power minus 5 kg meter per second, and Prandtl number is given as 0.7. So let's move to the solution. We have to calculate Reynolds number. Reynolds number is given by rho v L by mu. But in the problem, we are not provided with density. We have provided with viscosity. So we have to rearrange these equations. We will take this density down and divide it by viscosity. This term can be replaced by kinematic viscosity. So Reynolds number is velocity into length upon kinematic viscosity. From this, we will substitute the values of velocity, which is 13 into, and for length, which is 0.5 meter, and kinematic viscosity is given as 1.4 into 10 raised to power minus 5 meter square per second. So after solving this, we get the value of Reynolds number as 4.64628 into 10 raised to power 5. So after looking at this Reynolds number, we can see that the Reynolds number is less than 5 lakhs, from which we can conclude that the flow is laminar. Flow is laminar. So now that we have calculated Reynolds number, we will use Chilton-Colvin analogy for flat plates. So in our case, we are finding for mass transfer and laminar flow. So from the table, we can get the relation for Sherwood number equals to 0.664 into Reynolds number to the power 1 by 2 and Prandtl number to the power, Schmidt number to the power 1 by 3. So from this equation, we have Reynolds number, but we don't have Schmidt number. So first we will find how Schmidt number. Schmidt number is given by kinematic viscosity upon diffusivity. In our question, we have given with kinematic viscosity as 1.4 into 10 raised to power minus 5 meter square per second, and diffusivity is 2.5 into 10 raised to power minus 5. So after solving this, we get the Schmidt number as 0.61. So we will put this 0.61 and Reynolds number in this equation. So Sherwood number equals to 0.664 into 4.6528 into 10 to the power 5 to the power 1 by 2 into Prandtl number is 0.61 to the power 1 by 3, and we get our Sherwood number as from this equation as 383.708. So this is the Sherwood number that we get after solving the Chilton-Colvin analogy. So now we have calculated Sherwood number. From Sherwood number, we will calculate mass transfer coefficient. So Sherwood number can be written as Kc into LCH upon DAB, and the value of Sherwood number is 383.708. We have the value of length and we have the value of diffusivity. So all that left is mass transfer coefficient. So we will rearrange this equation into diffusivity upon LCH. Now we'll substitute the values of diffusivity, which is 2.5 into 10 raised to power minus 5 upon LC, we get it as 0.5. So from this, we get our mass transfer coefficient value as 0.01765 meter per second. So this is the value of mass transfer coefficient that we get for this question. So that now that we have calculated mass transfer coefficient, we have to calculate total water loss per hour per meter width of the plate. So to do that, we will calculate the molar rate molar rate of water moving out of the surface into the air, which is given by Na equals to Kc into delta C A. Here Kc into delta Ca can be, delta Ca is written as Cs minus C infinity. Here Cs is the concentration of water at the surface and C infinity is the concentration of water vapor in the air. As the water vapor in the air is considered negligible, so we will put the value of Ca infinity equals to 0. So Kc into Cs. But in the problem, we are not provided with the concentration of water vapor at the surface, but we have provided with the partial pressure of water vapor at the surface, which is 50 kilopascal. So by using ideal gas equation, we get it as Cs equals to Ps by RT. So here partial pressure of water is 50 into 1000 pascals upon R is the constant here, 8.314 into temperature, which is 305 Kelvin. So from this we have calculated the value of Cs, which comes out to be 0.0197 kilomole per meter cube. So now we have the value of Cs. We will substitute the value of Cs in the molar rate equation, which is Kc into Cs. Here we will substitute the values 0.01765 meter per second into 0.0197. We will convert this kilomole to mole, so we will multiply by 1000. So after this, we get the value of Na as 0.3477 mole per meter second. So this is the total water loss from the width 1 meter width per meter width per second. But we need to get the answer in kg per meter per hour. So to convert this unit to this, we have to multiply this value by molecular weight of water, which is 18 gram per mole, into, we also have to convert this seconds into hour, so we will multiply by 3600 seconds upon 1 hour, as 1 hour contain 3600 seconds. From this we will cancel the moles and the second. So after multiplying this, we get the value of 22.53 into 10 raised to power 3 gram meter hour. We can take this 10 raised to power 3 as kilogram. So 22.3 kg per meter hour. Na. So from this value, we get the total water loss per hour per meter width of plate in kg. So this concludes the part A of our solution. So let's move to the part B. So in part B, we have to calculate heat transfer coefficient, which is H, from the remaining value that we are provided. So to calculate heat transfer coefficient, we have to use Chilton-Colburn analogy, which gives us two equations, that is F by 2 Standard number for heat transfer into Prandtl number to the power of 2 by 3, which is J factor of heat transfer, and F by 2 equals to Standard number for mass transfer into Schmidt number to the power 2 by 3, which is J factor for mass transfer. For flat plate, these J factors are equal, so X by 2 equals to JH equals to JM. This condition is valid for flat plate. So in our question we have provided flat plate, so we will use this relation. From this we can substitute the value of JH and JM from this equation, which is Standard number for heat transfer into Prandtl number to the power 2 by 3 equals to Standard number for mass transfer into Schmidt number to the power 2 by 3. We will substitute the values of Standard number for heat transfer and mass transfer. So it is given as Nusselt number upon Reynolds number into Prandtl number to the power 2 by 3. And for Standard number for mass transfer, we can write it as Sherwood number upon Reynolds number into Schmidt number power 2 by 3. We can substitute the values of following dimensionless numbers, and by substituting the values of these numbers, we get it as heat transfer upon density into heat capacity into VCH. Here VCH is characteristic length into Prandtl number to the power 2 by 3. And after substituting the values of this dimensionless number, Kc upon VCH, this is what we get, into Schmidt number to the power 2 by 3. We can cancel out the VCH, and in this equation we have density, we have Cp, we have calculated Kc, we have Schmidt number and Prandtl number. So all that left is heat transfer coefficient. So we can find out this from this equation. So from this equation we have to calculate heat transfer coefficient. So remaining we will substitute, we will shift here Kc into density into Cp into Schmidt number by Prandtl number to the power 2 by 3. So we have to substitute the values. So here we have calculated Kc, Cp, we have the Schmidt number, Prandtl number, but we don't have density. But we have given with kinematic viscosity and viscosity. So from the relation of mu upon rho mu upon rho equals to kinematic viscosity, we can calculate density as mu upon kinematic viscosity. So we will substitute this here, kinematic viscosity into Cp. So I will just erase this into Schmidt number upon Prandtl number to the power 2 by 3. So now we have to substitute the value. From the part A, we have calculated Kc as 0.01765 meter per second into, we have viscosity as 1.6 into 10 raised to power minus 5 upon kinematic viscosity is 1.4 into 10 raised to power minus 5, and Cp we have given as 0.005 kilojoule per kg. So we'll also multiply by 10 raised to power 3, and we have to substitute the value of Schmidt number, Prandtl number. Schmidt number we have also calculated, which comes out to be 0.61 upon Prandtl number is given as 0.7. So to the power 2 by 3. After calculating these values, the H comes out to be 18.49 watt per meter square Kelvin. So this is the heat transfer coefficient that we have to calculate it. So it comes out to be 18.49 watt per meter square Kelvin. So this is the answer for part B. And here we have solved this problem. So let's move to the next question. A 1.5 meter long plate is exposed to an air stream at 290 Kelvin flowing at 4 meter per second. The surface of plate is initially heated but cools down as heat is transferred to air. The kinematic viscosity of air is 1.6 into 10 raised to power minus 5 meter square per second. The thermal diffusivity is 2.3 into 10 raised to power minus 5 meter square per second, and Prandtl number is 0.7. The heat capacity of air is 1005 joule per kg Kelvin, and the air density is 1.2 kg per meter cube. Calculate convective heat transfer coefficient if the plate has a heat flux of 500 watt per meter cube. Determine the surface temperature Ts. So let's understand the problem. In this problem, a flat plate is given as a flat long plate which has a length of 1.5 meter. An air stream is moving above the plate at a velocity of 4 meter per second and has a temperature of 290 Kelvin. We have given some data for kinematic viscosity of air, which is 1.6 into 10 raised to power minus 5 meter square per second. And we also have given thermal diffusivity, which is 2.3 into 10 raised to power minus 5 meter square per second. Prandtl number is also given there, 0.7, and heat capacity is 1005 joule per kg Kelvin, and air density is given, which is 1.2 kg per meter cube. And we have to find, first heat transfer coefficient, which is H. And in the second part we have given with heat flux, which is Q equals to 500 watt per meter square, and we have to find surface temperature of the plate. Now we have written the given data here. We will start with the solution. So first we need to calculate Reynolds number, which is given by velocity into density into length upon viscosity. We are not provided with viscosity, so we will convert this formula in terms of kinematic viscosity, which is given in the data. So the velocity of the air is 4 and length we have taken as 1.5, and kinematic viscosity is given as 1.6 into 10 raised to power minus 5. So from this we get our answer as 375,000, which is 3.7 into 10 raised to power 5. From this we can conclude that Reynolds number is less than 5 into 10 raised to power 5. From this we can see that the flow is laminar. So the flow is laminar. From this we can conclude that we have to use a laminar region relations or equations to solve this problem. So we have to find out the heat transfer coefficient. To calculate heat transfer coefficient, we have to use Nusselt number equals to 0.664 into Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. Here we will substitute the formula for Nusselt number, which is HLCH by K. Here K is the thermal conductivity, H is heat transfer coefficient, and LCH is characteristic length, which is 0.664 into Reynolds number to the power 1 by 2 and Prandtl number to the power 1 by 3. As we are not provided with thermal conductivity, we have to use thermal diffusivity by converting K into alpha rho Cp. So this is the relationship between thermal diffusivity and thermal conductivity. We will substitute the value of K here with thermal diffusivity into density into heat capacity. So write down the equation. Six four Reynolds number to the power 1 by 2, Prandtl number to the power 1 by 3. Now from this relation, H is here, we will shift this here and length is shift downwards. So 0.664 Reynolds number to the power 1 by 2 Prandtl number to the power 1 by 3 into thermal diffusivity into density into heat capacity upon length CH. Now we will substitute the values of Reynolds number Prandtl number, thermal diffusivity, density, heat capacity, and length, which is 0.664 into 3.75 into 10 raised to power 5 to the power 1 by 2. In Prandtl number, we have been with 0.7 to the power 1 by 3 into 2.3 to 10 raised to power minus 5. This is thermal diffusivity into density is 1.2 kg per meter cube and Cp is given as 1005. This whole is divided by length, which is 1.5. So after calculating these values, we get it as 6.676 watt per meter square Kelvin. So this is the heat transfer coefficient that we get after solving the equation. So this is the answer of part A. And the second thing that they are asking is, what is the surface temperature? Surface temperature Ts, and we have given with heat flux as 500 watt per meter square. So we will use the relation for heat flux. Heat flux equals to heat transfer coefficient into temperature difference. Here, heat transfer coefficient is 6.676 into temperature difference is temperature of surface minus temperature of air, and heat flux is given as 500. So heat flux value, air temperature we have given with 290 kelvins. So after, now we will substitute the value here. Ts equals to 500 by 6.676 plus T air, which is 290 kelvins. From this we get the value of Ts as 365 Kelvin. So this is the solution for part B, and we have solved this problem. From the first part we get heat transfer coefficient as 6.676 watt per meter square Kelvin, and from the second part we get the surface temperature as 365 Kelvin.